This conference will now be recorded.
That joined ISAC. She's a postdoc. She's joined ISAC last year in July in the frame of the Capitale Umano project related with the access research infrastructure. She's from Bolivia, from La Paz. She has a Bachelor and Master Science at UNSA, the University of Santander. Universidad Mayor de San Andres, and where she worked on VC properties in Chacaltaya and also in Europe. And then she did a PhD at the University of Grenoble, studying the air quality, air pollution in urban environments at high altitude. She's now working on the Era Urban project, but I give the floor to Valeria. Thanks for this presentation.
Thank you. Thank you for the introduction. As Angela mentioned, I come from Bolivia, and thank you for joining today to this seminar talk in which I would like to give you a broad description of the state of atmospheric research in Bolivia. As Angela has just mentioned, this is like a summary of my background. I did my bachelor's and master's in physics in the University of La Paz, la Universidad Mayor de San Andres. And during the PhD, my research topic was the air pollution in La Paz and El Alto, which are two high-altitude Bolivian cities. And as you can probably see from this slide, there's a common affiliation throughout my study years with the Laboratory for Atmospheric Physics, which is my home lab. And in order for you to understand what motivated my research topic during the PhD, I would like to give you a short overview of the atmospheric research that is happening in Bolivia and that is being led by this laboratory. So without further ado, I would like us to start this very short trip towards the Bolivian highlands. And as I was mentioning before, the LFA, or Laboratory for Atmospheric Physics, belongs to the State University within the Physics Research Institute. And it was founded in 1995, originally called as the Laboratory for Ozone Measurements, because the main focus of research of this lab was the measurements of UV radiation and the concentrations of ozone in the vertical column, because it had been observed that the doses of UV radiation in this Andean territory were very, very high, among the highest around the world. It has been observed that this phenomenon has its origin on purely geographic conditions. The combination of the latitude plus the high altitude of this Andean region makes the ozone layer to be particularly thinner in this area, which translates into very high doses of UV radiation. And towards the year, the research topics of this laboratory have expanded, and for which the name has also changed. Including radios on launching, LiDAR measurements, and a lot of scientific communication. And this is how LFA, in collaboration with many other research institutes around the world, under the wing of the Global Atmosphere Watch, were able to mount a station, a regional atmospheric monitoring station at Mount Chacaltaya. And to give you a bit of context of this measurement site, Mount Chacaltaya used to be, 50 years ago, used to be a glacier, covered by a glacier. Unfortunately, given the fast speed at which the glaciers are melting in this region, the glacier no longer exists. And the summit of this mount, which makes part of the mountains that form the Cordillera de los Andes in this region, is located at 5,400 meters above sea level, and the station was mounted slightly below the summit. As I said before, the measurements have been continuous since 2011, and this station was originally categorized as a regional station, but since last year has been upgraded up to global station. And in this map are shown the locations of all the global stations that make part of this monitoring network. I took it from the official site, but it has not been updated yet, for which I had to put the location myself. But we can see that with Chacaltaya, there are only 2 global monitoring stations that aim to provide a description of this very huge part of our continent. As I mentioned, which gives us an idea of the very big research gap that there is in this subcontinental area. And as I said before, Chacaltaya is located on it's one of the mountains of the Cordillera de los Andes that actually splits into branches when passing through Bolivia. So Chacaltaya is located on the oriental branch of the Cordillera, more or less 20 kilometers away from the second largest metropolitan area in Bolivia. And as can be seen in the map, represented by the colors, both cities are located at very high altitude with different topographical characteristics. On one hand, we have El Alto, which is located at the edge of the Altiplano region that is formed between the 2 branches of the Cordillera, and La Paz was built on the river valley right next to the Altiplano. And we can see how the topography in La Paz city can be also very complex. And in this photo, I like this photo because it shows the station, the house of the old ski station that was mounted in Chacaltaya when there was a glacier, but also gives us an idea of the view that we can have from Chacaltaya. The measurement site is located a little bit to the right. And the selection of the location of these measurement sites was not only based on the availability of almost ready-to-use facilities from the university that were already present there, but also because of, given the altitude of this mount, during certain hours of the day, the station is it's found outside the influence of the superficial mixing layer. And more or less what happens with Monte Chimone as well. And this would provide us insights not only on the local emissions, but also on long-range transport. And one of the sources that we were aiming to better investigate and comprehend were the emissions of regional biomass burning. Regional biomass burning is a yearly catastrophe that happens at the middle of the dry season, we could say. And to give you an idea of the magnitude of the emissions from these fires that are lit in order to get rid of agricultural waste, but also as a way of clearing the land for changing the land use. We have on the left an image of the territory of Bolivia just right after the end of the wet season, taken on the 10th of June of this year. And next to it, an image, a satellite image, taken of the same area during the biomass burning period. And we can see how the emissions of these fires not only affect the air quality at a subcontinental level, but also that these emissions can find its way through the Cordillera de los Andes and impact the air quality also on the other side of the Cordillera. And this is how it started my very first research project while I was doing the bachelor, which aimed to provide a statistical overview of the relationship between the carbon monoxide concentrations and black carbon concentrations that were measured during the first years of measurements in Chacaltaya. And as I guess you probably can already suspect, these tracers for combustions are not only emitted by regional biomass burning, but also by more local sources such as vehicular emissions. And it was seen from the beginning that Chacaltaya was constantly being influenced during certain hours of the day by these urban emissions, and this can be observed on this repetitive peak in concentrations of both pollutants that happens almost every day at the same hour. And this happens because as the surface gets warm, the mixing layer develops, to a level that it's able to submerge Chacaltaya and transport the urban emissions not only horizontally but also vertically. So it was clear from the beginning that there was a need for characterizing these urban emissions in order to better understand and decouple the local from the regional contributions to the station, and which is why the consortium that mounted the station in Chacaltaya decided to have a 2 years campaign of measurements of atmospheric particulate matter, describing their physical and chemical properties in the urban area. And at the end of this campaign, it started an overlapping campaign called the Salteña Project or Salteña Campaign, that in which even more instruments were added to all the stations in order to have a more comprehensive understanding of the atmospheric processes in all the three measurement stations. And these two campaigns, overlapping campaigns, ended up with a period of intensive measurements in which even more instruments were added to the set of instruments. This was only possible through the collaboration of several institutes around the world, among which is found CNR with ISAC and ISP. And what have we learned or studied so far from the measurements that were collected at Chacaltaya from the beginning? Well, the first things that we observed, as I mentioned before, is that there's a clear influence of combustion sources, not only coming from regional, but also from local emissions. We also saw that at certain hours of the day, especially during nighttime, the station is decoupled from the influence of the superficial mixing layer. We were able to see that Chacaltaya is a place in which frequent nucleation processes take place. And from the Salteña campaign, we were able to have deeper knowledge on what are the main sources contributing to what we measure in Chacaltaya on a regional level, a better understanding of the new particle formation processes. We were able to see that not only the lowlands are contributing to the measurements at this measurement site, but also that during certain periods of the year we have a shift in the dominance of the air masses coming from the Pacific that bring air masses from hundreds of kilometers away towards Chacaltaya, and that are able also to pick up emissions from different sources along the way, such as volcanic emissions that take place in the oriental branch of the Cordillera de los Andes, and more specifically in Peru. So this is more or less a summary of what has been studied so far in Chacaltaya, but we're still missing a characterization or a description of what is happening in the city of La Paz and El Alto, which make part of the same conurbation. And this is what motivated my research topic during the PhD. And the motivation was not only to be able to constrain the urban emissions or the urban signal from what is measured in Chacaltaya, but we saw that this was also important for the local population because air quality monitoring in Bolivia is still in a very precarious state. And even though there are some air quality regulations and policies put in place, there had never been a study that aimed to understand what are the sources that are contributing to the atmospheric pollutants present in our atmosphere, and which is essential in order to implement efficient air quality policies. And from a urban perspective, it is very important to characterize these sources because studies have shown that the short-term and long-term exposure to PM particulate matter is associated to morbidity and mortality of cardiovascular, cerebrovascular, respiratory diseases, and also that the effects on health that is exposure to pollutant can even begin before we are born. Moreover, according to the WHO report, the latest report, it has been estimated that air pollution is responsible for several millions of premature deaths around the world, but the majority of these the burden have taken place in low to mid-income countries, among which Bolivia is categorized. So this is why the objective of our study was to identify and characterize the sources of particulate matter that are affecting the air quality in this conurbation. And we also intended to assess what is the impact of these pollutants on the health of the local population, as well as to, we wanted to provide a baseline for air quality onto which air quality policies could be advised. And we evaluated the state of air quality in this region based on, through the lenses of 3 air quality parameters that I will briefly describe now. The first one of them is particulate matter, which is, I guess, most of you are familiar with, and it's the most widely used indicator for assessing health effects when exposed to air pollution. And it's also regulated in most of the countries around the world. And the latest report of the WHO has provided some threshold values above which we can expect some adverse health effects. And in terms of PM10, for example, the WHO recommends that the exposure should not exceed the 45 micrograms per cubic meter on a 24-hour period for more than 3 consecutive days. And on a yearly average exposure, the level should not exceed the 15 micrograms per cubic meter. The problem with this metric is that the health effects that are a result of PM exposure not only depend on the amount of particles that we're breathing in, but also on the size of these particles, on their chemical composition, on their morphology. And unfortunately, this metric is dominated by the mass of the coarse particles, which are often the least harmful in terms of health. The second parameter is oxidative potential, which is a metric that is gaining a lot of strength, especially here in Europe, which basically measures the ability of PM to produce reactive oxygen species. And we talk about a state of oxidative stress when the presence and production of these species is not it's found in an imbalance with the anti-inflammatory response from our body. And this metric is one of the most relevant, is considered one of the most relevant indicators of PM toxicity because it's closely related to the biological pathways through which particulate matter can produce adverse health effects. And the third parameter are carbonaceous aerosol particles that are labeled differently depending on the technique that is used to measure them. But for the sake of this presentation, I will just refer to them as black carbon. And by black carbon, I mean particles that are efficiently absorbing radiation in the visible spectrum, that are a byproduct of incomplete combustion. So they are particles that are have a thermally stable structure. They are small enough to penetrate deep into the lung. They are often used as tracers for combustion and anthropogenic activities, and their capability to absorb radiation is so strong that they are considered important short-lived climate forcing agents. So now passing to the sampling sites, we mounted 2 urban background stations that were located, as I mentioned before, nearly 20 kilometers away from the Chacaltay station on a horizontal distance. And vertically, there's a difference of 1 to 1.5 kilometers difference in altitude. The first station was located in the facilities of the International Airport in El Alto, and the other one was mounted on the rooftop of the building of a playground that was located on the top of a hill within downtown. And different techniques, offline and online techniques, were used to assess the state of air quality. So as part of the offline sampling, we collected 24-hour samples every third day using a PM10 head inlet at the beginning of the campaign during the first 15 months. And then during the second part of the campaign, we changed the inlet to measure PM10 or to collect PM 2.5 particles. And then after sampling, these filter samples were stored and then transported towards Europe, where they were weighted and fractioned in order to have them analyzed for different species. The analysis was performed for different plateaus of 3 different research institutes, and we obtained a very broad chemical speciation that included 178 different chemical species. Then also we had some extra analysis of some fuel samples that were taken pre-combustion. From the same filter samples, we measured the oxidative potential through 3 different acellular assays: OPDTT, OPIA, and OPCFH. And for each assay, a different type of antioxidant is introduced. And then the interaction of the antioxidants with the ROS, oxygen species, produced by the extracted particles from the filter samples, is detected using different optical techniques. And these different assays of measuring OP are sensitive to different components of PM, for which they can be considered complementary. But unfortunately, the OP activity that was measured through this assay, through OPIA, displayed very low values, very close to the detection limit, for which we decided to exclude these measurements from the analysis. Finally, we measured black carbon concentrations throughout the entire campaign using etalometers, which basically measured the change in attenuation that is produced by the presence of particles that are collected onto a filter matrix. And these changes in attenuation are then translated into absorption coefficients and equivalent black carbon mass concentrations. And at the end of the campaign, as I said before, we had collocated measurements performed by some SP2s that measured the mass of these individual black carbon particles based on the incandescences that these particles emit when they are heated to very high temperatures. So having had an overview of the sampling methodology, we can start with some results. First, we can evaluate the concentration levels of PM10 in the urban region. We see that they exert a clear seasonal variation, being maximum during the dry season and minimum during the wet season. And we see that in general, the daily concentrations do not exceed the 45 micrograms per cubic meter threshold advised by the WHO, but we are on a yearly average, we are far from reaching or complying with the 15 micrograms per cubic meter advised by the WHO. And these measurements, since they were collected on a 24-hour period, cannot provide us an insight on the diurnal variation of these atmospheric pollutants, for which we use black carbon concentrations as a way to investigate what is this diurnal variation. And we see that as well as PM, black carbon concentrations exert the maximum values during the dry season compared to the wet season, but that these concentrations are strongly dependent also on the intensity of the emissions, and this can be seen when comparing working days to Sundays. Still, throughout the day, we can always see this bimodal pattern throughout the day, in which the maximum of the day is reached during the morning when people start their activities. They decrease as the boundary layer develops, and then the concentrations increase once again during the evening as the mixing layer re-stratifies and coinciding with the second rush hour emissions.
Valeria, excuse me, what do the colors refer?
I'm sorry, I missed the label. So, thanks. In blue are the measurements in El Alto, in green are the measurements in La Paz, and in red the measurements in Chacaltay. Thanks for the question. And if we compare the fraction of BC compared to PM, we observe that BC makes less than 5% of the PM concentrations. So now that we have an idea of what is the state of air quality in terms of these two air quality parameters, we can start to investigate what are the main emitting sources of these atmospheric pollutants. And for this purpose, we made use of the broad chemical speciation that we have in this period, and also making use of the positive matrix factorization tool through the software of the US EPA. We perform this factor analysis following a multi-site approach, meaning combining the data from both cities in order to give more strength to the statistical analysis. And we were able to obtain a stable solution with 11 factors or 11 sources identified by applying very soft constraints. And here are the results of this factor analysis. These are the 11 sources identified. And the first thing that we can observe from this analysis is that almost 50% of the PM concentrations that are measured in PM10 concentrations that are measured in this conurbation come from local sources. Being one of them, and even the first one, the dust that is resuspended by natural and anthropogenic processes near the urban area, but also a large fraction can be attributed to the ensemble of vehicular emissions. Then we see that the secondary aerosols make part of the remaining 25%. We observe the presence of the some primary biogenic emissions. And we see that agricultural biomass burning or regional biomass burning, as I described before, on a yearly average has only an impact of 8%, a contribution of 8%. But during the biomass burning season, this contribution increases to 13 to 17%. Then, through this analysis, we were able to identify a very small source in terms of contributions to total PM, but it's very important when we take a look on the chemical profile, because we see that it's responsible for the majority of the organic compounds that have been shown to be hazardous for health. And if we take a look from the black carbon perspective, we can see, based on the optical properties of the black carbon measured in this region, we see that first, the angstrom exponent that gives us an idea of the mixing state of the absorbing aerosol particles. We see that it's very close to 1, which is a typical value for fresh emissions. And the same can be observed from the mass absorption cross-section that gives us an idea of the aging of the particles. So these two optical properties, what they are telling us is that the main sources of absorbing aerosols in this conurbation come from fresh emissions that have similar characteristics as vehicular emissions. And this is coherent with what we saw in the results from the PMF. And if we try to apply two different source apportionment methods, the first one is the typical etalometer method that is applied to the etalometer measurements, which showed that if we split into wet season and dry season contribution, this method is able to shows us that there seems to be a contribution throughout the year, like a slight variation of the contribution throughout the year, but this is not what we really expected, because the biomass burning source is a seasonal source. The thing is that this method is limited to only 2 sources of carbonaceous aerosols, but from what we have seen from the PMF results, we see that we not only have vehicular emissions and biomass burning emissions, but we also have this factor that is emitting a large concentrations of absorbing aerosols that is called waste burning. And we also have a large presence of dust in this area that in some, depending on the chemical composition, dust can also be light absorbing. And for this purpose, we decided to try a different method that allowed to distinguish between more than two sources contributing to absorption. And for this, we decided to apply a multilinear regression associating the absorption coefficients that were measured by the etalometers on one side as variable to be explained with the temporal series of the different sources contributing to PM as explanatory variables. And we can see that, coherent with the previous results, traffic emissions seem to be the dominant source of absorbing aerosols. And we also see the contribution of biomass burning in producing absorbing aerosols, but we see that waste burning can represent a significant source of absorbing aerosols in this area. And we followed a similar approach in order to understand what were the main sources of the third air quality parameter, which is OP. And if we take a look of the ranking of the sources identified by the PMF, it's very different from the ranking of the sources identified or responsible for the OP that is measured in this site. We see that here dust is the dominant source, whereas in terms of OP, traffic emissions and biomass burning seem to be the most hazardous for health. So combining these three perspectives of air quality parameters, we decided to go one step further and to perform an epidemiological study using a very basic model in epidemiology, associating two health outcomes, one acute respiratory infections and the second one pneumonias on the left side of the equation, and associating them with the air quality parameters that we have measured in both urban areas. We decided this model was adjusted by seasonality and meteorological parameters in order to eliminate the bias this could introduce in the model. And in order to be coherent with the previous studies, we also followed a multi-site approach. But since we can see there are some clear differences in meteorological parameters, but also health outcomes between cities, for which we included the city as a source of random effect. And the main results of this analysis showed that we could not find clear associations when associating PM10 concentrations with these two health outcomes, whereas when we compare them with PM2.5 concentrations measured in the urban area and also the OPDTT that was measured from the same samples, we see a very clear tendency and also a significant association between acute respiratory infections and the activity of OPDTT at 3 different lags and with PM2.5 at 2 weeks lag. We also see this tendency with black carbon concentrations, but the associations were not significant. And if we replace, instead of the exposure, instead of putting the observations, we put the results of the PMF, we were able to see that dust was showing a significant association with a delay of 2 weeks with respect to acute respiratory infections, and also traffic was showing a clear significant association. So what we can conclude from all these different analyses of the state of air quality in this area is that the air quality in the region of La Paz and El Alto is mainly affected by local sources. And we see that the population would rapidly benefit from the reduction of vehicular emissions that from all perspectives seem to be the most significant in terms of air quality. But we also saw the need of an identification and mitigation of this waste burden factor. And here I should clarify that in La Paz, in Bolivia in general, waste burning is not a way of dealing with trash. So it's not like the official way to get rid of trash, which is why we suspect that this could be related to isolated events that take place in different parts of the city. But we cannot rule out this could also be associated to the emissions from the industry that is mostly concentrated in El Alto. We saw that also that a reduction in biomass burning emissions would immediately improve the air quality in the entire country. And up to here, we have limited our study onto the particulate part of air quality, but they're still missing the part of the gaseous component. And here finishes what I have done in the past, and which brought me back here to Italy. And I will briefly tell you what I'm doing here now. So I'm working with Angela, and I was included in this pilot study that it makes part of the ARI Urbans project, in which we are looking forward to be able to map the black carbon concentrations in the city of Milan. And the objectives of this study is to explore the spatial distribution of these black carbon concentrations, as well as identifying the possible urban hotspots of pollution. And we also want to explore this possibility of expanding the coverage of the measurements by involving citizens in the collection of the measurements. The measurement site is, of course, Milan. And here are plotted all the routes of the delivery packages. Oh, I forgot to mention, sorry. So the sampling was made involving a group of delivery couriers that work for this company called UPM that transport and deliver the packages using bikes. And these are all the routes that they took during the measurements period that covered an area of 25 kilometers, more or less. And the experiment consisted of 4 seasonal campaigns in which for 2 weeks, DC concentrations were measured using portable samplers during working hours. And we would equip the bikes, as you can see in this picture. We would place a GPS and 2 black carbon portable samplers when available in the back pockets of these bags, with the inlet facing the riders in order to also assess their exposure while they work. And very briefly, some very first results, we see that as expected, the near road exposure or near road concentrations of BC are higher than the ones measured by urban background stations. But that this difference also depends on the season, and not only on the season, but on the hour of the day, being maximum during winter at the early morning hours. And the first results of mapping of BC that we were able to produce from these measurements show us here in blue the measurements, the normalized black carbon concentration, normalized by the seasonal median. And we see that when the normalized concentrations are below the median BC, we see sort of scattered distribution of the measurements. Whereas when we take a look on the measurements that are above the median BC, we can clearly outline the arterial ways of Milan, including the beltways and the radial streets. And with this, I would like to conclude, and thank you very much for your time and for your attention. I don't know.